Okay, this is page 191. And this is called natural logarithms. Natural logarithms. Natural base exponential functions are exponential functions with base e. And that's like a lowercase cursive e. E is a common irrational number that is approximately 2.71828. So you know how when we did common logarithms last class? Common logarithms have a base of 10, okay? If you have a natural logarithm, that means you have a base of 2.71828 approximately. This number occurs so often, like in math and science, that it got its own little symbol, okay? Because it occurs a lot. I don't know, maybe in science class y'all have seen this before. Has anybody seen E in science, lowercase e, cursive e? Okay. These functions are useful for describing continuous growth or decay. Exponential functions with base e have the same properties as other exponential functions. Okay, so remember the other day when we were taking notes on exponential growth and decay, and we were talking about investing money, or we were talking about populations increasing or decreasing, and we had those formulas that we used. And if you go back and read those notes, it said that's the formula you used. Like if the if you're talking about interest, if it was just compounded 1 year, okay? Well, if something is continuously compounded, that means it's constantly being calculated. You're going to use a very similar formula, but it's different, okay? And this formula, it does have this natural base in it, okay? So it's different because it's not compounded once a year, it's compounded continuously. So this is the formula for continuously compounded interest. Did everybody get what's above? Okay. It's A of t equals P times that little cursive E, meaning 2.71828, natural base, raised, I should have given myself more room, to the R times T. Make sure that looks like it's in the exponent on your paper. So A of t is the amount in the account after t years. P is the principal. That's the same thing as the initial amount, okay? So if it says what's the principal, that's like the initial amount deposited, just like on the problems we did the other day. We already know that E is a natural number, meaning approximately 2.71828. But we don't have to type that into our calculators because our calculators have that E on them, okay? R is the annual interest rate converted to a decimal. So in the last equation that we did, we had 1 plus R or 1 minus R. Now R is in the exponent, because this is calculated differently than it was before. Mr. Brown gonna come mess up my video. And T is the time in years. Good morning. Not much, just making a video here. You want to be in the video?
Hey, this is going to be the most awesome video ever. Pert. Awesome. Continuous interest.
Yeah.
That looks like an L. That don't look like... Oh, wait. I pointed there. It's on the screen.
Here.
This is the neatest thing ever. That's an E, not an L, guys.
Yeah.
Just so y'all know.
Lowercase e.
Yeah.
It was kind of
She
tall.
just can't make it, right?
Yeah,
Now this is going viral because I'm here.
probably.
Tens of bazillion people are going to be watching this.
Probably like 4, but
I'm
That's
here for
cool.
it. Have you done your RVT?
yes.
Okay.
I did that days ago.
Days ago.
You're welcome.
Love y'all. Be good.
All right, anybody still writing? All right, page 192. We're going to do a word problem that uses this equation. Suppose you won a contest. We're lucky, I guess. Suppose you won a contest. At the start of the 5th grade. That deposited $3,000. That was a sweet contest. To an account that pays 5% annual interest compounded continuously. As soon as you see that it said compounded continuously, you know that you don't use the same formula as that I taught you already in this section. The one was like A of t equals A times, open parentheses, 1 plus r raised to the t. Yes?
Do you have Rudy?
Yes?
Can you send him to the test, please, for checkout?
Sure.
Thank you.
You're welcome. But it's, again, as soon as you see compounded continuously, not the same formula. Totally different. So compounded continuously, period. How much will be in the account in 4 years? There you go. Make sure you check Edmodo. Thank you. Round to the nearest dollar. So I'll show you after we do this. We won't have to write it down. But I'll show you if it was just compounded once a year, how it makes a difference in how much is in the account. Now, it might not make a huge difference in 4 years, but in 30 years, the longer the time goes by, the bigger a difference it's going to make. Compounded continuously is going to make you more money than just compounded once a year. So let's write our formula down, which was A of t equals P times E. Try to make it more like an E instead of an L, apparently, raised to the R times T. So we're looking for the amount in the account in how many years? 4 years. So we're looking for A of 4 equals, what would my principal be? 3,000. You don't substitute in anything for E. E is its own number. Okay? That's not a variable. It represents a number. Raised to the rate times time. What's my rate as a decimal? 0.05 times time of 4 years. So multiply 3,000 times E first. Anyone? No, I don't. First of all, exponents come before multiplication. And in my exponent, there's parentheses that I need to simplify. So let me do that. 3,000 times E raised to the 0.05 times 4 is going to give me 0.2. Please be careful and try not to put that all in your calculator at once. Chances are good you're going to make a mistake because you're going to forget to put parentheses. So just go ahead and simplify it first. Now, do I multiply 3,000 times e, or do I raise e to the exponent? E to the exponent. If you have a graphing calculator, I want you to do this with me. Turn it on. His name is Wade. Could have gotten up, just saying. Yeah. Down the left-hand side, where you see log, and then one key below that, it's LN. That stands for natural logarithm, by the way. But above it in blue, it says e raised to the x. So that's what I want. I want that e, and then I'll put in a number for x, okay? It's in blue, so I've got to push the second button first, and then that button. So my screen should look like this. E raised to the x. So it put the e in for me, and then I have to give it the variable of 0.2. So e raised to 2/10 is approximately, I'm going to, of course, leave this in my calculator, but on my paper I'll just round. So e raised to the 0.2 is approximately 1.22. And then I can multiply by 3,000. So if I just leave that big number in there, I'll round at the end. So that number multiplied by 3,000. And it did say round to the nearest dollar, so that's going to be $3,664. There will be $3,664 in the account in 4 years. Cool beans? So now if that was just compounded annually, you don't have to write this, I just want you to see the difference. If it was compounded annually, it would be a of t equals a times 1 plus r raised to the t. So that initial amount times 1 plus the rate raised to 4 years is 3,000 times 1.05 raised to 4 years. So 1.05 raised to 4 years times 3,000 would give me $3,646. Compounded continuously, it was $3,664. Same amount of money, same amount of time, same interest rate, but the more often they calculate your interest, the more money you have, which makes sense. If they only calculate interest once a year and put that money in, compared to if they compound your interest constantly, then you're getting paid on your interest more often, so it's going to grow faster. So even though that's only 20-something bucks, or a little less, more, whatevs, in 4 years and 30 years, that's going to make a whole lot more difference than in just 4 years, okay? The longer you wait, the more of a difference it'll make. Anybody have questions on that? Anybody still writing? Page 193. We are almost finished with section 9. We have natural logarithms and we have to graph logarithms, which we may get done today, I'm not sure. So we're going to have a test coming up real quick. Next week's going to be weird with the testing at the beginning of the week, so I don't know exactly when right now we're going to have it. Let's see how far we get today. The exponential function y equals e to the x has an inverse. The natural logarithmic function which y'all know what the inverse is going to be, my x and y will switch, right? The base will stay where it is, but where there's a y, I'll put an x. Where there's x, I'll put a y. So it's x equals y. Whoops, I wrote that wrong. X equals e raised to the y. Sorry about that. So this is exponential function. This is still an exponential equation, but it's an equation of a logarithm, okay? So this is the exponential form of a logarithm, which is log base e of x equals y. Logarithmic form, exponential form, both of a logarithm. This is an exponential function. When the base of a logarithm is e, we call it a natural logarithm. So y'all know the other day when we had a base of 10, that's called a common logarithm. Well, if you have a base of e, we call it natural logarithm. And instead of writing log base e, we just write ln. So when you see ln, like we just saw on the calculator, that means log base e. But instead of writing log base e, you just write ln. That means natural log. That means log with a base of e. A log with a base of 2.71828, whatever it was. Okay? But you're not going to see it written as log base e. You're going to see it as ln, which means natural log, log base e. So, log base e of x equals y is the same as natural log of x equals y. They mean the same thing. You're not going to see it written as log base e of x, okay? So that ln button on your calculator, that means log base e. Y'all are pumped up today. And then one more little thing, which I've already said, there is a natural logarithm button, or a key, on your calculator. Anybody have any questions before we start solving equations that have a natural logarithm? Yes, ma'am.
Could you explain, could you just explain the whole thing again?
Just explain the whole thing.
Not the whole thing, but like the first part.
Up here? Okay. You know that logarithm is the inverse of an exponential function, right? Inverse means the x and the y switch. So when we switch the x and the y, it looks like this. Well, when you see that e written down there as the base, e means the number 2.71828. That's what it means. But it occurs so often that they just gave it a symbol. Okay? So this is the exponential form of a logarithm. This is the logarithmic form of a logarithm. We need both of these forms to help us solve logarithms, okay? So that's all I was saying there. And then I was just saying that if you do have a logarithm with a base of e, you're not going to see it written as log base of e. You're going to see it written as ln. That means logarithm that has a base of e. We just write it natural log instead. That's all it means. Instead of log with a base of 2, it's log with a base of 2.71828. Okay? So we have the same thing applies. We're doing the same rules, same thing as when we solved logarithms before. It's just you have a base that's a symbol. It means 2.71828. Approximately. It goes on after that. All right, solving an exponential equation. Is it hot in here?
Yeah.
Tariana, can you turn the dial, please, to the left? Thank you. Solving an exponential equation. First example. E raised to the x minus 2 equals 12. Can we write both sides with the same base? Can we write e and 12 with the same base? No. Okay, so we know from before, if you can't write both sides with the same base and it's an exponential form, we'll convert it to logarithmic form, right? So, of course, we're going to make a note of that. Since we can't write both sides with the same base, write the equation in logarithmic form. Bless you. I can't emphasize enough how important these notes are to y'all. I know you think it's boring as possible. I get that. But I still have students from previous years coming to ask me if I have a spiral, one of my previous notebooks that they can have to keep so they can have it in their math class, use it for their next math class. So I'm telling you, especially if you're going on to pre-calculus or if you're taking the college algebra, probably not so much for prob and stats, but the maths that you take after that, they're going to expect you know all this stuff. If you keep this notebook and you've taken good notes, then you're going to be able to go back and review, okay? So don't throw it away at the end of the year. I know you're probably going to want to burn it because you're so tired of taking notes, but trust me, you're going to want to keep it for later on. Bless you. Okay, so I would write this as log base e. Really, I wouldn't, but I'm going to do it right now because that's how we're used to seeing it. Log base e of what number? 12 equals x minus 2. Bless you. But we don't write, if your base is e, we don't write it like that. We write natural log of 12 equals x minus 2. This is the correct way to write. It's the correct way to write a natural logarithm. Now, we can simplify the left side. We're going to need our calculator to do that, okay? You're going to need a calculator to do that. We can just put natural log of 12 in our calculator, but don't use the log button because this log button is going to give you a base of 10. It's for common logarithms only, okay? You need a base of e. So you have to use the natural logarithm button. You don't hit the second key because that's going to give you e with an exponent. You want to take the natural log. You got to turn it on first. Natural log looks like this of 12. The natural log of 12 is approximately I'm just going to put 2.48 on my paper. And I just said put ln, meaning natural log of 2, in calc, meaning calculator. So 2.48 approximately equals x minus 2. Then to solve for x, we'll just add 2 to both sides, and x is approximately 4.48. Anybody have questions so far? All right, page 194. We have 2e raised to the negative x equals 20. 2e raised to the negative x equals 20. Can we write both sides with the same base? No. Is it an exponential form? Does 2 have an exponent of negative x? No, only e has an exponent of negative x. So we can't rewrite this in logarithmic form while this base is being multiplied by 2. Okay? A lot of kids think that this is exponential form, but it's not, because this base has a different exponent than e does. If there was parentheses around it, that'd be one thing, but there's not. Okay? So to get it in exponential form, we're going to have to do what? Divide by 2. And remember, you can't convert it to logarithmic form until it's in exponential form. So that's going to give me e to the negative x equals 10. Okay, so now that it's in exponential form, I can rewrite it in logarithmic form. So that's log base e of 10 equals negative x. Now, you don't have to do this step. You can go right to the natural log of 10 equals negative x. I just do it so I don't get confused. Yes?
Do you have Travis Douglas in class?
He's not here today.
Okay, thank you.
You're welcome. Natural log of 10 equals negative x. What I was saying was, I just do this step so I don't confuse myself. You know what I mean? But you could just go straight to the natural log of 10 equals negative x. Because I like to follow the same order each time. So I like to do this step, then do this step. So what are we going to do next? Put what in the calculator? Natural log of 10. Put it in the calculator. Natural log of 10 is approximately 2.3 equals negative x. Is that my answer? Nope. What do I got to do? Divide by negative 1. X is approximately, because I rounded, negative 2.3. Easy, right? How about this? E raised to the 3x. Then I've got a plus 5 that's not in the exponent equals 15. Is that in exponential form? No, what should I do? Subtract 5. So e raised to the 3x equals 10. Can I write both sides with the same base? Nope. So I'm going to, it's in exponential form right now. Still a logarithm because x is an exponent. We are going to convert it to logarithmic form. So that's log base e, which is the same thing as natural log. What are we taking the natural log of? 10 equals 3x. We just took the natural log of 10 on the last example, so I already know that's 2.3 equals 3x. Divide by 3. And x is approximately 0.77. Next example. Does anybody have questions on that one? Anyone? We have 4e raised to the 2x, there's no parentheses, plus 2 equals 16. Can I convert that to logarithmic form the way it is? No. It's not in exponential form yet. So how should I start to get this in exponential form? Subtract 2 from both sides. So we have 4e raised to the 2x equals 14. So I subtracted 2, not divided by 2. Now is it in exponential form? What do I do? Divide by 4. So now I have e raised to the 2x equals 14 divided by 4 is going to give me a decimal. Notice we have a lot of decimals. Yeah, and that's okay. Oh, I forgot. No, e raised to the 2x equals 3.5. Now can I write both sides with the same base? No. So I'm going to have to convert it to logarithmic form. So you can say log base e of 3.5 equals 2x, but really that's natural log of 3.5 equals 2x. That's how you're supposed to write it. Evaluate natural log of 3.5 in your calculator. What'd you say? 12.5? Oh, okay, I was going to say 1.25 equals 2x. And then I will divide by 2. And x is approximately 0.63, I'll go with. I've got a word problem for you, and then I'll give you your classwork. Anybody have a question? Okay. Looks like I need to get a new spiral over the weekend. So, do you remember back on page 181, we have the problem that says, using the example above, how many years will it take to get $800 in the account? So in that one, it gave you the $800 and it did not give you the time. That's what they were looking for, right? And I told y'all, I said, what we know now, we kind of have to guess and check how many years it will be. And I showed you how to put it in the calculator to find the table of values. I said, but once we learn logarithms, I'll show you how to solve a problem where when you have a variable in the exponent, okay? Well, now's the time. That's why we need to know logarithms, is for when we have variables in the exponent. So, in this example, using the word problem, from page 181, evaluate the same problem using what you know about logarithms. And I just reminded you that it asked how long it would take to get $800 in the account. So what we did before was we made a little table of values. The previous example, we knew how long it took to get, how much money we had in the account in 5 years, which was $593. So we knew it had to be more than 5 years. And so I showed you how to put it in a calculator and look at the table of values. But here's how we would solve it using logarithms. All right, is this an exponential form? No. What could we do to get it in exponential form? Divide both sides by 500. And so you get 1.6 equals 1.035 raised to the t. Now, this is not a natural logarithm, right? This is not a base e. I'm going to do a word problem where we have a base e, but this is not it. So now, can we write both sides with the same base? Nope. So we'll convert it to a logarithm. Log base what? Here's my base. 1.035 of 1.6 equals t. What do we do now? Change a base. So remember, you have to do log of 1.6, close parentheses, divided by log of 1.035. In your calculator, you got to have a calculator for this. And so you get 13.66. Does that mean in 13 years you're going to have $800? Yeah, that's like 13 years and 7 months. So if it asks what year, it would be, you would probably put 14 years. Remember, when we did the problem, in 13 years you had $781.98 because it calculates it at the end of the year. At the end of the 14th year, you had over $800. It said how long will it take to get 800 in what year, so we would put year 14, okay? So let me just do another one real quick where you have a base of E. If you deposited $3,000 into an account earning 5% annual interest, compounded continuously, how many years would it take to earn $10,000? So because it said compounded continuously, we don't use the same formula that we did on the previous example. We use the compounded interest formula, which is A of t equals P, remember that's principal, times E raised to the R times T. So we want to know the amount in the account after T years. Do we know the amount in the account after T years? 10,000. That's what we want to know, how long it takes to get 10,000. So instead of like A of 5 years or A of 10 years, we want to know how long it will take to get 10,000 in the account. Equals, what's my principal? 3,000 times E, you don't plug anything in for E, raised to the rate is 5%. What will I put for that? 0.05. Do I know time? That's what I'm trying to find. So 0.05 times T is just 0.05 T, correct? Now I could use guess and check, or I could plug the equation into my calculator. You would want to put 10,000 in there. You'd put Y equals just the right side and look at the table of values, but we know how to do logarithms. So we want to get this in exponential form. What would we do? Divide both sides by 3,000. 10,000 divided by 3,000 is 3.333 equals E raised to the 0.05 T. Is it an exponential form now, or do I need to do anything else? It's not. It is. It's good. So it's going to be log base E, which we know I'm running out of space, so I'm just going to write, that means the natural log of what? 3.333 equals 0.05 T. What do I do now? Find the natural log of 3.333 in the calculator. Approximately 1.203 equals 0.05 T. Of course, we want to know what time is by itself, so we're going to divide by 0.05 And the time that what I get is 24.077. So at the end of the 24th year, we're not going to have exactly $10,000 in there because it spills over into the 25th year. Okay? So your answer would be 25 years. Sometime in that 25th year, you're going to get it. At the end of the 24th year, you're not going to have 10,000. You're going to be close, but because it spills over into the 25th year, you got to say your answer is 25. Does that make sense? Yes, Miss Rayleigh. Awesome. Anybody have any questions?